Vergleichungsexamen. Yeah, wir haben right out here the semester after this stuff like it's like
Oh, great. So yeah, thank you, Ocean, for coming in for inviting me. I'm really excited to get to hear this talk and to see what you guys get on with during today and what Portland design to love with or applications values. I'm Cameron. I'm work for Infleqtion. Inflection's a global quantum technology company. So we develop all sorts of quantum technologies, really with the aim of driving the go forward on what technologies can make seismic shifts in how we do things across the globe. That could be in defense, in energy, in healthcare, in day-to-day lives. So what I wanted to talk to you today, what we'll work out what it does is it's only going to be a whistle-stop tour, and I'm very happy to answer questions at the end, and I'll be milling around with ready to have a chat and get to know it and understand the thoughts and ideas you're having on the apps. So I'll start off describing Infleqtion, and then give a whistle-stop tour of quantum computing. Now, this is a topic that can fill either undergraduate courses, master's courses, PhDs, a lifetime of postdoctoral research. I'm going to try and condense it into about 5 minutes, so we'll see how I get on. And then what I think you guys are probably more interested in is what impact is this going to have for healthcare. I'm going to focus mainly on higher mental analysis because I think that's where quantum computing is really going to shine, maybe less so on the sort of on the patient side of things and more on the background analysis. But yeah, I'll continue some of the examples of the work that Infleqtion had done in this field already, and the ideas that we have going forward, where we're actually looking for collaboration, so we can discuss that later as well. And for a bit of background, I'm a mathematician by training. I got lost when I ended up doing some research in physics. Then spent some time working as a machine learning consultant, actually. So doing several large. I'm assuming you guys are going to be trying to implement today. During my time there, we tried quite a lot to get into the healthcare world, the health tech, but we're struggling for various reasons. I then left and now run the software team at Infleqtion, where we look after both the sort of quantum computing side for also our sensing businesses, and still looking at some machine learning applications and how we can use our technology across different applications. So here on Infleqtion, this is an example of some cool pictures of the source of showing which this is more of a module slide for investors to and you didn't be able to pass in depth. We are spread out Dubai, so we've got several offices in the US. We've got an office in Oxford, and we've got an office in none of the States. And really, as I said, our goal is to use quantum technology and particularly atom-based technologies. So this is taking individual atoms, either isolated or in clouds, manipulating them, generally using background using lasers, in order to derive some sort of useful output that can accelerate applications. So we're a team of physicists, mathematicians, engineers, and we work for all sorts of companies within the US and the UK. In terms of locations, this is a fun slide to show various places in the US, obviously the UK, Australia. We've recently shipped a functional keys to Japan, and they actually use our technology on the International Space Station in some of their cold atom experiments up there. So the ISS have various physics experiments going on from the International Space Station, and one of the technologies they use is our patented vacuum system that allows essentially anyone with a few bits of kit to set up a tracked atom system. Simple to the point that they use it in undergraduate labs in some universities. So this is really taking the core technology that mean internally build on to make up the rest of our products. And then basically giving that to either users in, say, universities or in this case the International Space Station. before I head on to that, I thought I had another slide. I'm talking about what are all these technologies? So the big one that everyone thinks about, or gets a bit shout about most, is quantum computing, and so this is what I'll talk about in a bit more depth, and that's can be this revolutionary model of computing that is unlike anything we've had before, and will provide orders of magnitude improvement for certain applications. But in fact, I just focused on quantum computing. We also built a clocks. I imagine most people have heard of atomic clocks, as atomic clocks are the reference standard for how we keep time across the globe. And so we are developing the next generation of atomic clocks for various disease cases. Until I joined Infleqtion, I didn't realize that people would get so excited about atomic clocks and the different types of clocks and the different use cases for different clocks that you would have. One of the big drivers for this is to reduce dependence on GPS. That lowest timing around the UK, in fact around the globe, is done via GPUs. So everyone's devices will be calling out, so the satellites to tell it all the timers. For your phones, it doesn't matter if that get interrupted briefly, or you lose signal, or hit some limited actor tries to spoof by GPS. But if you're working in energy, if you're working, imagine healthcare to certain situations, if you're working in financial services and your timestamps start to go up, that can be a massive issue. That can cause blackouts in a worse situation, and the energy sector, for instance. The other technologies we work on are a little bit more R&D at the moment, but they're starting to come into production. Those are inertial navigation systems. So this is when essentially you use individual atoms that you fire through a tube to act as a gyroscope. So this is to detect rotations and accelerations so that you can navigate, again, when you don't necessarily have GPS. So if you want to know where you are based on when you started and what motion you've gone through, you need to be able to track that motion really well. And that's what you need these gyroscopes. Classically, we have various approaches to doing that, but we're starting to show that atoms are a really good way of doing that. One example of where this is being used at the moment is actually to navigate on the lungs of underground. Because I've seen under several hundred meters of Earth, there's no GPS, and actually people don't know where everything is at least. We don't know exactly where all of the tunnels are, where all the pipe work is, and so we're sending quantum sensors underground on rail cars to try and work this out. And finding the other one that's quite exciting at the moment is detecting radio signals. So if you want to detect the radio signal, you normally need a massive antenna. Radio waves have by large frequencies, so to detect those frequencies, you need quite large antennas. And in certain situations, you might not want to have a several meter long pole stuck on whatever you're working on. Say if you're in a car or one radio or whatever, you want to be a bit more mobile. So what we've actually developed is it's actually a lunchbox that uses individual atoms when we excite them, so they almost ionize and strip their electron quite far away from the center of the atom, and at that in that configuration, they're very sensitive to radio rays, and so we can detect the radio rays by how the atoms behave. And so this is again another example of how quantum technologies are breaking down the barriers that classical technologies about. You being able to shrink several, possibly multiple antennas on the order of meters long down to a small lunchbox and a computer that you stick in a rack. So with the other technologies out of the way, I'll then talk about quantum computing. The quantum computing, as I said, is a revolutionary mode of computing. It is completely unlike anything we've had before. It's not sort of like your transition from CPUs to GPUs to TPUs that you're hearing about in the AI space. Fundamentally, quantum information gives us a new paradigm that we haven't had before. So in classical computing, we work with switches. Everyone's familiar, I imagine, with sort of the idea of binary numbers. We have zeros and ones. In a computer, those correspond to switches that are on and off, and switches are controlled by electrical symbols. In quantum computing, you can have a situation where, because of the rules of quantum mechanics, you can have 0 and 1 at the same time. And you can actually bond some types of 0 and 1 at the same time. And all of this sort of space of information that you can harness, at least for one qubit, is described by the surface of the sphere. So rather than just having 2 points, which we would normally associate with 0 and 1 at the top and bottom, you actually this whole sphere information states that you can pack your data into. What's even better is that because of quantum entanglement, which is this phenomenon that Einstein famously coined as spooky action at a distance, where you can take two quantum decisions, you can entangle them together, and then, in principle, whatever distance they are separated, they're still joined through this quantum entanglement. And it means that action on one affects action on the other. What's even better about quantum entanglement is that your amount of states that you can access starts to scale. So in a single qubit, you can have a 0 state or a 1 state, and you can have these combinations of 0 and 1s. When you have when you have 2 qubits, you can start to get multiple states. So you've got an up, a down, an up, down, up, and then you've got all of the individual combinations of those. So that's what I've sort of shown as these adding together. And what this allows you to do is, if you think of your state, your information space in classical computing is growing as you add more bits, more bytes up to gigabytes, etc. The quantum information space is growing exponentially. So, and eventually, people are familiar with exponential curves. It gets quick. It gets big pretty quick. For instance, the example that's given is that if we could get 300 qubits working perfectly, and that's a catch, then that's essentially more states in your quantum space than there are atoms in the known universe. And that gives us a massive range of opportunity to use that information space, embed data in it, and perform computations in it. Now, I'm not going to dig into all of the details of how we do that coding and what you can do theoretically in that space, but I would like to bring it back down to earth and show how do we do that. Like, I can give you all the maths behind quantum computing, but I don't think that's really what's interesting. What I think is really cool and hopefully interesting for this audience is how we actually do it. So on the side here, this is a scary diagram that scared me, because I'm not a physicist, but basically describes all of the atomic states in, I think, a cesium atom. I heard it's and these are the atoms that we use in our quantum computer. So in our quantum computer, we take a load of cesium atoms, potentially initially thousands. We cool them down, first of all using magnets. You can trap these atoms using magnets that confine them into essentially a ball. And then you cool them down with lasers. So that's where we've got polarized laser beams coming in. We've got magnetic fields generated by the currents and some wires around it. And this essentially starts to cool the atoms, because the atom's momentum is reduced by the laser beams. There are other further processes that go on, but essentially the light hits the atom, and the atom slows down as a result of receiving the momentum from the light beam. And this allows us to get to microkelvins of temperature in an atom cell that is essentially in a vacuum in a glass box that's, I don't know, a few inches wide. We don't have to have any cooling. We don't have to have any fridges. We're cooling these atoms down purely with lasers and magnets. Once we cool them down, we then start shining even more lasers on them, basically to allow us to access more of these transitions. And once we can access these transitions, we can manipulate the state of the atom to start to do cool things. So once we've got it cool, we're normally in one of these two states, the 0 or 1 state. And so we've cooled these atoms down, and then we apply what I would describe as just an egg box. So you imagine having an egg box shape in your atom cell, and the atoms fall into that web. And that's what gives you this image on the side here, where we trap our atoms, we apply a lattice essentially, and the atoms fall into that lattice and then trapped. And because of another rule of physics, when you have atoms in this lattice, you either have one atom or you have 0 atoms. You can't have 2, 3, 4, 5, which means that when we trap our atoms, we are trapping individual atoms in this array. And so the array there was a picture from our machine in the UK. We've now actually got it bigger, so we've got to about 60 by 60 arrays of atoms. And then what's even better is that we can take another beam, and I think, I don't know that, transition on them. There should be a beam that says none of fund. And we can pick up these atoms and we can move them around and we can put them back down in the array. So we can actually start to individually, and call them tweezers, pick up all of these atoms, and that allows us to move atoms towards other atoms to be able to interact with. And then we use more laser beams again to interact them. Once we've got those interactions, we can start to do these computations, etc., that allow us to make use of these atoms as qubits to do computation and get some results.
Sorry, quick question. So, yeah, qubit, in the case, say what a qubit is made of from one atom, or does it have to be completely off one?
So each of the atoms, well, once we've done our preparation, so we've cooled it down, we've run it for this array, we then have to do some more preparation to make sure it's in exactly the right state. At that point, we call it a qubit. And then we have, okay, so in this picture is what, 6 by 6, that's 6 qubits. That same machine has scaled up in the last month to have 10 by 10 atoms. So that's 100 qubits in our array. And I guess for reference, that picture, that array fits in the width of a human hair. So this is obviously very small. We're talking individual atoms, but we can fit quite a lot of those in quite a small space. The computer itself, at the moment, this is our machine in Oxford, which we're very proud of because it looks very neat. We have another machine in the US that looks significantly less neat, so I show you pictures of this one instead. We have these are essentially massive things, probably about the size of our 2 tables that we've got set up here, that are on compressed air springs to isolate them from the ground. Because you can imagine if we're shining lasers, individual atoms in a space smaller than a human hair, and you have some vibration, mainly because then setting up a new building next door, your lasers wobble and Mr. atoms, and the machine doesn't work. So everything's isolated from the floor. There's some cracking around the edge again to exclude more fields. So we make sure that there's no stray magnetic fields, electric field, etc. We've got some control racks around the edge. There's houses loads of control electrodes. We've got loads of laser systems in here, and then this is where the magic happens. And right in the center of this paper here is our little cell that's a couple of inches by a couple of inches, which is a vacuum, and inside that is our atoms. So with that, for the soft floor of what quantum computing is, how we make it boards of pizza, I wanted to come to how we're going to use quantum computers to accelerate environmental analysis. Now, as I'm sure I do into lecture this room on the challenges in bioanalytical analysis and the challenges in healthcare in general. But there are broadly 4 categories of applications that we think quantum computers are probably going to start to provide benefit for. The first one is machine learning, and that's an example that I'll dig into a bit more, give a concrete example. But broadly speaking, machine learning is obviously making waves across the board, and there's good evidence that in certain applications, quantum computing can enhance those machine learning techniques even further. Essentially, if you imagine when neural networks that are the backbone of machine learning at the moment, you can add a quantum equivalent of that either before or after your standard neural network. I get some really interesting results. HSBC actually published this week a result where they used that for algorithmic trading and managed to get, I think, a 34% increase in how effective their algorithmic trading was, which is, if you're a bank and you're able to boost your profits by 34% by adding a new computer in, that's quite massive. On optimization, this is looking at things like scheduling problems. I'm sure in all of your lives of work, and you're familiar with scheduling problems from hospitals, from GP practices, etc. And this is an area where we are already starting to see quantum computing provide measurable improvements on how big a scheduling problem we can solve. One of the challenges with scheduling type problems is that as you add more and more complexity, more and more constraints, more and more options, the search space gets so huge that it's just impossible to solve. And so we tend to either make approximations or we simplify the problem in some way. What quantum computing is going to allow us to do is to actually solve those really difficult versions of that problem in a reasonable time. So this might be that we're looking at how we schedule beds in a hospital, or how we plan transport for either for patients or for or planning utilization of surgery rooms. There's all sorts of applications there. On the chemical one side, this is actually what quantum computers were originally designed for. When Fire came up with the idea of quantum computer back in the 60s, I think it was 50s or 60s, he wanted to build a machine that we could use to simulate quantum systems. Well, all of our chemical interactions are quantum systems, so let's use a quantum computer which already is behaving in a quantum mechanical way to simulate their systems. And then the next step up from modeling some individual molecules is to do larger scale material science applications. One that we've been even looking at here is superconductivity, trying to find how we can get better superconducting materials, higher principal temperature, or if we can do some clever things with lasers, some techniques to try and effectively shine a laser at zero and it becomes superconducting for a short period of time. Trying to understand that, that's so that's where we're hoping to move to with quantum computing. Some insight that I remember to show you is some work that we take with a company called Avatrial in Cambridge, where they have some multi-omics data that they're looking at. They're trying to use machine learning to understand cancer-specific data, mainly cancer, but also other disease mechanisms. And because of the complexity and how large this data set is, as you try and include more and more features and more markers from these data sets, it just becomes too difficult to compute. What we wanted to test out with Avatrial was to see, can we take those data sets, pipe them through our full computer, and either find some new insights or improve the insights that we're already getting. And what we found was really exciting. I thought I was going to jump into the results then. Anyway, this is probably what we did. We like some data. That's the size of the data, various omic data. I'm sure you guys know far more about omic data than I do. The me, this is all just numbers in a table. We tested it. Flight Jason, this is what Avatrial were already doing. So you take that data, we through some machine learning models, and then we're doing unsupervised learning to try and understand what the possible markers could be. The reason we used unsupervised is that we didn't necessarily know what individual patients were either presenting with, or if they had any diseases that we were trying to uncover. All we wanted to do is understand what were the patterns in the omics data. And so we're doing some unsupervised clustering. This is how we describe quantum circuits, which is essentially how you program these quantum computers. This is basically saying, let's try and do what is essentially kernel method. You're familiar with that from classical machine learning. And really, what we're doing here is building a neural network out of the qubits that we've got, so within the quantum computer. And then we got some really interesting results from the science in it. So we found this, it wasn't the quantum or the classical results either did any better necessarily. We have an idea of what clustering we were expecting to see, and most of them probably picked out the markers that we were expecting. What was really interesting was that when we were using the quantum approach, we got more consistent enrichment. So this is where it's picking up things across more of the omic data sets than the machine learning cluster. So the machine learning is on the edge here, and you're picking up on some of them, but the quantum ones, mainly the middle one, was picking up on far more. Basically trying to pick up on far more markers and make the connections between those markers. So this was really interesting. It was only a very short project that we worked on this one in the UK. Our team in the US are doing a much longer project at the moment with the US government, doing essentially something very similar, looking at how we can apply these methods to sample data from healthcare applications, with the idea that if you could start to if you can understand these clusters, then you can start to use those clusters to do predictive analysis and say, okay, well, which of these clusters are actually markers for disease mechanisms, etc. And that's the set we hope to make next. And so with that, with that, that's I just want to say I hope you have a really good rest of your day, and I'll be around. I'm very happy to answer questions. Imagine probably not now because I don't really got another good speaker, but certainly throughout the day. So thanks very much. That's up.